Have you ever asked yourself a question which you knew to be kinda weird, but which you wanted to desperately know the answer to anyway? Something like, which color are mirrors? What was the best thing before sliced bread? Or is there a synonym for the word synonym? I agree, these are super big questions and maybe you have given it a quick Google and tried to answer them. But what if Google does not give you an answer? This is exactly the situation where scientists find themselves in. Luckily for them, they are quite stubborn and will not easily take an "I don't know" for an answer. One of the questions they have been trying to answer for more than 100 years is: what is the smallest thing in the universe and how does it work? Not that they did not find any pieces of the answer at all in that century, by the way. They did, just not the final complete answer. However, science being science, the found answers are all guarded by some evil masks that don't make it easy to understand them. Maths is, however, just a language, and, just as any other language, it can be translated. So instead of looking what the math says, we can look at what it tries to say. So let us do that. Welcome to the world of particles, and welcome to Fundamentally Explained. Physics tries to understand how the world works. You can approach this quest from multiple angles. You can choose, for example, to look at everything around you and carefully study everything. But, as you might have noticed, there's an incredible amount of stuff in the world. Studying everything would take an eternity. Instead, you can also look at the smallest puzzle pieces that make up this stuff. Compare it to Lego buildings. Yes, you can study every building ever made, but you could also study the individual bricks. If you understand those, you, in principle, understand every building ever made, and every building that will ever be made. And even more important, although there is an infinite amount of buildings you can make, there's only a limited amount of types of Lego bricks. This is exactly the approach physics takes when it tries to study the smallest stuff that exists. Instead of studying candles and pot plants and books and my dinner of yesterday and why it was the worst pasta I ever made, it studies the stuff that all these things are made out of. This stuff, the Lego bricks of the universe, are called particles. Although, okay, let's study those particles then, sounds like a good plan, nature makes it very hard to do so. They are just so small, seeing them becomes really hard, even for the best microscopes in the world. Because of this, scientists have to make specialized contraptions and machines that make it possible to detect these particles anyway. These technologies then sometimes find their way into more practical applications like MRI machines in hospitals or the camera in your mobile phone. Just detecting a particle, however, is not enough. Compare it to taking a photograph of something like the monster of Loch Ness. A single photograph will convince nobody of the existence of Nessie. It could just as well be something that looks like the fabled animal. Also, even if it were truly Nessie, from that single photograph you cannot see how she behaves. If you want to know that, you would need more photographs or something like a video. The same holds for particles. To prove their existence and to understand how they behave, we need to see particles more than once, and in very controlled circumstances. The experiments that create these circumstances for small particles are, ironically, almost always extremely big. One experiment in Argentina, for example, that detects particles coming from space has a surface area of 3,000 squared kilometers, or 1,100 squared miles. Another experiment in Japan is basically a tank filled with 50,000 tons of water. Both these experiments essentially wait until a specific particle passes and leaves a sign of its existence in the experiment. This is all fun and games if the particles you're looking for are abundant enough, or are enough inclined to leave such a sign. But if you're looking for really rare particles or particles that only rarely leave a sign, you might just be waiting for the rest of your life. So, instead of waiting for a particle to be detected, scientists also try to make these particles themselves by using machines called particle colliders. Particle colliders take known particles and accelerate them to almost the speed of light. This takes some time, but when the particles finally have their maximum velocity, they are smashed headfirst into each other. This collision is so violent that all the energy that is involved gets crammed into such a small point that it forms new particles. How it does this, or even why it does this, nobody knows. We just know that energy can be exchanged for particles as long as you have enough of it. The particles that originate from these collisions are therefore not just the remnants of the original particles, but actually newly created particles that did not exist before the collision. These new particles can be detected using the specialized machines mentioned before. These machines can easily become tens of meters or tens of yards long and equally as high. But in essence, they are nothing more than enormous cameras, specialized in seeing particles. Because of experiments like these, we know of the existence of 17 particle types. The theory that describes these particles is called the Standard Model, which is, if you ask me, the lamest name they could have ever come up with for a theory that ought to describe how the friggin' world works. Oh, Mr. Scientist, congratulations on becoming a father, and what a beautiful daughter you have. Oh, thank you. What's her name? Standard, baby. What? Anyway, if we ignore the name for the moment, the Standard Model describes 17 unique particles, 17 types of building blocks out of which the universe is made. Each of these has its own properties and its own behavior. Some particles, for example, have mass, while others don't. Some are electrically charged, others aren't. But even though 17 is not a very large number of unique particles, the Standard Model explains a lot. For example, it explains what electricity is and how it works. It explains what light is and why you can see stuff with it. It explains why atoms form and why they behave like they do. The theory has been tested with experiments, of course, but none of these have been able to break the theory, to catch it red-handed when making an incorrect prediction. But even though we can't find any mistakes in it, we know the Standard Model is wrong. The goal of the model is to describe everything, but it doesn't. It does not contain gravity, for example, nor does it give an explanation for something scientists call dark matter, a substance that seems to form 85% of the mass in the universe. This would mean that the Standard Model only describes 15% of everything there is, which you can barely call everything. It also has some theoretical problems that theorists can't seem to find a nice answer to. So how can the Standard Model then truly be a theory of how the universe works if it has glaring issues? Because of this, we want to know nature's answers to these issues. We know that nature works. We just don't understand it well enough yet to encode it correctly in a theory. This is exactly why we do those experiments. If we either find a new particle, an 18th Lego brick, or find unknown behavior of the particles we do already know, we get a hint on how to fix the model and thereby improve our understanding of how the world works. But experiments cannot do this alone. To design a good experiment and to sift through the enormous amounts of data that they produce, you need to know what you want to look for. Although we don't know what we don't know, of course, we can try to make educated guesses. This is done by developing new ideas, possible solutions to the problems of the Standard Model, by investigating the theory that we already have. These ideas are then captured in new theories that can suggest the existence of new particles or new behavior of known particles, which can then be tested with experiments. The results of these experiments then influence the creation of new ideas that can then be captured in new theories. Experiments can then test these new theories, which influences the creation of new ideas, and so on and so on and so on. Particle physics theory and experiment are therefore both needed. They are closely interwoven and share the same goal: finding new things we don't understand. Truth be told, however, there is no guarantee we will find anything. The whole endeavor of particle physics is exploration in its purest form, driven by the curiosity of the world and the universe we live in. On this channel, we will use this same curiosity to continue our journey through the world of particles. If you like this video, give it a thumbs up and consider subscribing, because you don't want to miss the next video. We will have a look at the Standard Model and ask ourselves the question: But wait, what is a particle then actually? I know it sounds complicated, but don't worry, it will all be completely understandable as it will be fundamentally explained. See you next video.